When you hear the term game of life, you probably think of the classic Milton Bradley board game. However, the game of life that we're talking about today is something entirely different.
The game of life is a mathematical game that was devised by mathematician John Conway in 1970. Conway had set out to create a cellular automation that generated interesting and random patterns.
Cellular automaton sounds complicated, but really it's pretty simple. A cellular automaton is a grid of cells in any finite number of dimensions, where each cell has a finite number of states, and moves between these states according to the states of its neighboring cells.
To start an automaton, you have to assign a state to every cell. Usually every cell in the grid is in the default state, and you assign different states to a select few. Then you simply let the automaton run, and at each step, known as a generation, each cell either changes or doesn't change its state based on the cells around it. In the game of life, we have a two-dimensional grid of cells, each of which is either on or off. Each cell either becomes alive, stays alive, or dies based on the following rules. First, a live cell with less than 2 live neighbors dies due to underpopulation. Second, a live cell with 2 or 3 live neighbors stays alive. Third, a live cell with more than 3 live neighbors dies due to overpopulation. And finally, a dead cell with 3 live neighbors becomes alive due to reproduction.
The starting pattern for the game is called the seed. Once the seed is set in place, each cell in the grid is set to either dead or alive based on a function according to the rules of the game. With only 4 rules and a simple starting seed, the game of life can generate unique and complex patterns in just a few generations.
Shapes of live cells in the grid are often called patterns. These patterns have been sorted into categories, such as still lives, patterns that do not change between generations, oscillators, patterns that cycle between variations of the starting pattern, spaceships, oscillating patterns that move across the grid, and finally glider guns, fixed patterns that generate bullets that move across the grid.
Some examples of still lives are blocks, beehives, loaves, boats, and tubs. Some examples of oscillators are blinkers, toads, beacons, and pulsars. Some examples of spaceships are gliders, lightweight, heavyweight, and medium-weight spaceships. And some examples of glider guns are Gosper and Simkin.
The applications of the game of life extend far beyond simple experimentation in the study of cellular automata. Here's a fairly simple idea. If we have a starting pattern and an ideal ending pattern, how can we make sure that our seed will eventually morph into the target pattern? It turns out we can't. This is known as the property of undecidability, which in this case means that if we have a starting and ending pattern, there is no algorithm that exists which can tell us if the ending pattern will ever appear.
One of the fundamental concepts that underlies all of computer science is known as a Turing machine. A Turing machine is a theoretical machine that reads and writes symbols from an infinite piece of tape according to some preset rules. Any computer algorithm can be simulated on a Turing machine by representing its logic as a state machine. The game of life can be used to construct a pattern that functions as a universal Turing machine, which is a Turing machine that can be fed instructions to simulate another Turing machine on any given input. This means that the game of life can theoretically be used to simulate anything, even an entire computer system.
For example, this means that the game of life can be used to prove any algorithmic property that a Turing machine can. For instance, the halting problem, that asks if a program can be written that receives other programs as input and determines if they halt or if they run forever. We can use the game of life to prove this quite trivially.
Let us define S as our starting pattern, which is a universal Turing machine with some arbitrary input. If this Turing machine indeed stops, meaning it doesn't run forever, then there must exist a halting state. We can represent this as our ending pattern, P. It doesn't matter what P is, simply that we can prove its existence. However, as we know from before, there is no algorithm that determines whether a starting pattern S will generate an ending pattern P, and therefore there exists no algorithm to determine whether a given program will halt or if it will run forever.
The game of life can also be used to simulate Boolean logic. Therefore, theoretically, any logic-based circuit can be created with the game of life, ranging from a simple flip-flop transistor to a full-blown computer processor. At first glance, the game of life is a very simple concept to understand. It is a cellular autonoma with a two-dimensional grid, 2 states per cell, and 4 simple rules governing the behavior of each cell. Despite such a simple formulation, the game of life provides not only an intriguing time sink that generates hypnotic patterns, but also a potent mathematical device which can be used to simulate physical and theoretical concepts alike. From theory centered entirely around the game itself to constructing infinitely open-ended computational machines, to inspiring infinite complex variations, to providing challenges for dedicated puzzle solvers, the game of life has it all, cementing itself as one of the most interesting, useful, and awesome inventions of the 20th century.